Force is the thing that can cause acceleration. Force is what causes acceleration. One of the most important ideas that we see in physics 2201. First, remember what we mean by acceleration. Numerically, it's the rate of change of velocity. And when we say force can cause an acceleration, what we mean is that force can cause a change in velocity. Any kind of a change in velocity. It might involve speeding up. The change in velocity might be slowing down, or the change in velocity might be a change in the direction of the velocity vector. Any of those or combination of those is an acceleration. In everyday speech, acceleration is usually synonymous with speeding up, but in physics, acceleration refers to any kind of velocity change. Whenever we're dealing with a situation involving forces and accelerations, and we're trying to figure out what's going on, the first thing that you need to do, always, is to recognize what forces are present in that situation. And to do that, you need to have some idea of what forces you should be looking for. That's why it's good to have that list of forces that's there in the Chapter 4 folder in Blackboard. If you don't have it with you right now, stop the video, make yourself a copy of that list. The things I'll be describing in this video are some elaborations on what is in that list. The list is a good outline of the following video. So the first force that one should always be on the lookout for is a force that's almost always there: weight. Weight is just a name for the gravitational force from the Earth, the gravitational force from the Earth that is pulling down on anything that has mass. Usually our algebraic symbol for the weight force will be capital W, and there's at least for situations near the surface of the Earth, there's a simple rule for calculating the size of that gravitational force from the Earth, the size of that weight. It's just mass times g, where g is the acceleration caused by gravity, 9.8 meters per second. It's important to note, it's very important to note, and it's very easy to forget that weight is not mass. It's very easy to confuse those two. Try your best not to confuse them. Weight is not mass. Weight is a force, like I just said here. Mass is not a force. It's something quite different. So when you get into problem solving involving forces and accelerations, a common mistake when you're doing the algebra is to write weight as just mass. But they're not equal. That's not true. Sometimes people will write weight as just the acceleration due to gravitational force. That's not true. Weight is mass times acceleration due to gravity. So that's one force that you should always be on the lookout for. It's almost always present, and it always involves, weight is always a force that pulls a mass toward the center of the Earth, and down is just another name for towards the center of the Earth. So weight always is a force that pulls down. The second type of force is a much more broad category. It's called elastic forces. One specific kind of elastic force would be the force that comes from a stretched or compressed spring, or anything very similar to a spring. A spring force is a kind of elastic force. Elastic force is a force that comes from any elastic object, and to at least a certain extent, almost all solid objects are at least a little bit elastic. By elastic, we mean that if you squeeze the object, it'll try to snap back to its original larger size. If you stretch an object, it'll try to snap back to its original smaller size. If you twist an object, it'll try to snap back to its original untwisted state. That's what we mean by elastic. Whenever you distort it in some way, it tries to return to its previous undistorted shape, its previous undistorted state. So for example, a spring, let's imagine a spring that's tied down, fixed to a wall at one end, and then the other end is free. And if the spring is neither stretched nor compressed, it's this long, so the right-hand end of the spring would be right there. But then let's imagine that you pull on that end of the spring. You stretch the spring. So the end of the spring has been displaced in this direction this far. There's the displacement of the right end of the spring. But because the spring is stretched, and because it's elastic, it's going to try to snap back to its original shorter length. So if you're still holding on to this end of the spring, while the spring is trying to snap back to its original shorter length, this end of the spring will be pulling on your hand. There's a spring force from the spring on your hand pulling that way. If you pull on the spring pulls back on you. When the spring is stretched, the spring tries to make itself unstretched. The rest of the spring is pulling on this end of the spring, trying to pull it back to its original location, and as a result, the spring is pulling on your hand. Similarly, here's the left-hand end of the spring tied to the wall. Here's where the right-hand end of the spring would be if you just left the spring alone. But now imagine that you push on the spring, push it to the left, you squeeze the spring, so that now the right-hand end of the spring is right here. The right-hand end of the spring has been displaced to the left by this distance. But being elastic, the spring is going to try to snap back to its original longer length. And as this piece of the spring tries to snap back this way, it's going to push this way on your hand. So there's a spring force from the spring pushing on your hand. As you push on the spring pushes back on you because the spring is elastic. A third type of force is the so-called normal force, and a normal force is actually a kind of elastic force. N is our usual algebraic symbol for a normal force, and here's an example of a normal force. I push on the blackboard, and as I push on the blackboard, I can feel this part of the blackboard bending a little bit. This part of the blackboard is bent. There's a little bit of a dent in the blackboard right here, but because the blackboard is elastic, it's going to try to snap back. That indented part here is going to try to snap back to its original perfectly vertical plane. And as that part of the blackboard tries to snap back this way, it pushes on me, pushes this way on me. And that push from the blackboard surface is a normal force on me. A normal force is, to make a long story short, a push from a surface. And notice in this case, the surface was vertical, and the push from that vertical surface, the push from the blackboard on me was horizontal. That's always how a normal force works. The push from a surface, and the push is perpendicular to the surface. In this case, vertical surface, horizontal push, horizontal normal force. That's always the way a normal force works. So for example, if I just have a book sitting on a table, there is, of course, weight. Weight is, of course, a force pulling down on that book because the book has mass. But in spite of that downward pull from gravity, the book isn't falling, it's just sitting still. That means there must be some upward force that cancels out the effect of this weight force, so that the overall force, the grand total force on the book, is no force at all, zero total force. And that force, that upward force that cancels out the downward force of the book's weight, is a normal force from the tabletop. A horizontal surface producing a force perpendicular to that surface. There's a simple example of a normal force. One step more complicated. Imagine now two books piled on top of each other. This original book, call it book 1, and then another book, call it book 2, and let's think about all the forces acting on book 1, just the forces on book 1. There is still the weight force, the Earth's gravitational pull on book 1. And just as before, there's still the normal force from the tabletop pushing up on book 1. Book 1 still is not falling, it's just sitting still, so we know there has to be some upward force pushing up on book 1 to counteract all the downward force. But now there's another force. There's also a downward push from the bottom surface of book 2 on book 1. The bottom surface of book 2 is a horizontal surface, and it pushes vertically on book 1. So a horizontal surface pushing vertically, that is a surface pushing in a direction perpendicular to the surface, that's another normal force. A normal force from book 2 pushing down on book 1. We know that normal force from 2 pushing down on 1 has to be there because book 2, of course, feels a weight force pulling down, but book 2 is not falling, so there must be some upward force on book 2 that keeps book 2 from falling, and that upward force on book 2 would be a normal force from the top surface of book 1 pushing vertically, pushing up on book 2. But where does that force from book 1 on book 2 come from? Remember how we get normal forces. Book 2 pushes down on the top surface of book 1. That makes, by pushing on the top surface of book 1, the top surface of book 1 is no longer perfectly horizontal. There's a tiny little dent in that surface, but it's still elastic like most solid objects, so it's going to try to snap back to its original perfectly horizontal shape, and as it tries to snap back, it pushes up on book 2. In other words, because book 2 pushes down on book 1 pushes back, pushes up on book 2 in exactly the same way that because I pushed on the blackboard, as a result, the blackboard pushes back with a normal force, pushes back on me. That particular style of thinking is something that we'll see over and over and over and over again. The first few times you hear it, it may be a little hard to follow, but like I said, you'll see it over and over and over again, and eventually it's something that you'll get used to. But anyway, normal force basically is caused by the elasticity of the surfaces that are doing the pushing and getting pushed on. One more kind of elastic force is a tension force. T is the algebraic variable for the tension force, and the tension force comes from ropes and chains or rubber bands or things like that. Just imagine this. You've got a vertical rope and you hang some mass on the bottom end of it. That, of course, stretches the rope a tiny little bit, but the rope, being elastic, is going to want to snap back to its original shorter length. And in trying to snap back, it's going to pull up on this mass that was hanging from the bottom. And that upward pull from the rope on the mass that's hanging is the tension force. The tension force is always a pull from some kind of a rope or chain or rubber band or muscle. It's always a pull from something that has been stretched and is trying to de-stretch, trying to snap back to its original shorter length. And in trying to snap back to its original shorter length, it pulls on whatever it was that was stretching it. Next, there are 3 different kinds of friction force. All friction forces are forces that come from some surface and act on another surface, because whenever 2 surfaces are in contact, there can be adhesive bonds between the molecules on one surface and the molecules on the other surface. And in order to get those 2 surfaces to move with respect to each other, you have to break those bonds. It takes some effort to break those bonds, and therefore there's a force, a friction force, that makes the motion more difficult. One type of friction force happens when the 2 surfaces are sliding across each other. Imagine, for instance, got a book on a tabletop. You just give the book a push and it starts moving with some velocity to the right. But the bottom surface of the book is sliding across the surface of the table, and there are adhesive bonds between the surface of the table and the bottom surface of the book. Those adhesive bonds slow down the book. It make it more difficult for the book to continue moving. So the book eventually slows down to a stop. In other words, that force from the surface across which the book is sliding, acting on the bottom surface of the book, since it's a force that is slowing the thing down, it has to be a force that pushes backwards. So the friction force is like that. Just to keep everything clear, whenever I'm talking about a friction force, I'll always use lowercase f. Capital F refer to other kinds of forces, but lowercase f always friction force. And then to distinguish one type of friction force from another, I use subscripts. K for the friction force of sliding, because Sometimes that force is also, the sliding friction force is also kinetic friction. Right? Kinetic means movement, and so this is a friction force that you get when one thing is moving, sliding across another surface. And the friction force always points opposite to the velocity of the sliding thing. So for example, let's say I've got a big crate and I'm trying to push it across the floor. So there I am pushing, and as I push the crate moves with a velocity from left to right. And what are the forces on the crate in that case? There is, of course, weight, the gravitational force from the Earth pulling down, pulling straight down, pulling towards the center of the Earth on the crate. And since the crate doesn't fall, we know there's a normal force from the floor pushing up on the crate, a horizontal surface pushing in a direction perpendicular to the surface. That's a normal force. So normal force from floor on crate. There's a second normal force. There is a normal force from my hands pushing on the crate. My hands are a vertical surface, and they apply a horizontal push to the crate. Right? A surface pushing in the perpendicular direction, that's another normal force. Normal force from my hands on the crate. And then, as the crate slides this way, there's a kinetic friction force, a sliding friction force, opposing that sliding motion, opposite to the direction of the sliding crate's velocity. So in this particular situation, 4 different forces acting on the crate. Kinetic friction, or also known as sliding friction, that's one type of friction force. Second type of friction force is called static friction. Static means unchanging, and static friction is a kind of friction that happens when a thing is not moving. Static friction force is a force that prevents sliding. Kinetic friction happens when there is sliding. Static friction is what's going on when you would expect sliding, but the sliding is prevented. For example, imagine a crate on an inclined surface. You would expect gravity to make the crate slide downhill, but sliding in this direction is being prevented. That's because there's a static friction force, the adhesive force between the molecules of the incline and the molecules on the bottom surface of the crate. Those adhesive forces are strong enough to keep the crate stuck and keep it from sliding down. Static friction force always points opposite to the direction of the sliding that it prevents. In this case, downhill sliding is being prevented, which means the static friction force is pointing uphill. And just for completeness, let's put the other forces on the crate into that drawing. There is, as always, the weight pulling straight down, pulling towards the center of the Earth. And again, there is a normal force from from this surface, from the incline, pushing on the crate. Surfaces, when surfaces apply normal force pushes, those normal force pushes are always perpendicular to the surface. So that means that in this case, since the surface is this way, perpendicular to this means this way. The normal force from the surface on the crate points diagonally because the surface that is doing that perpendicular pushing is also diagonal. So those are two kinds of friction force, kinetic friction and static friction. There's one more, rolling friction. Whenever a wheel is rolling, instead of sliding, you have rolling friction. Rolling friction, just like static friction, prevents sliding. But whereas static friction prevents sliding and keeps the thing from moving at all, rolling friction prevents a round thing from sliding, but allows the round thing to roll instead of slide. Lowercase f and subscript r for rolling friction. Let's just imagine one of the lab carts that you've been working with. There it is. And there's the wheels. And you give the lab cart a push so that the velocity is in this direction. Well, here's the track that the lab cart sits on. Two things you can imagine two different things happening to the wheels. They could either roll clockwise as the cart moves forward, or if this were a really greased up, slick track, the wheels might slide instead of roll. If the wheels were sliding, of course, they'd slide that way. Just like on a really icy road, your car is moving this way, and if the road is really icy, the tires, instead of rolling, will just slide forward. But the wheels are rolling instead of sliding. Rolling is being prevented, or sliding is being prevented. Sliding is being prevented, and you get rolling instead. That means there's a rolling friction force that's, first of all, preventing sliding, and secondly, making the wheels roll. In the case of static friction, the static friction force pointed opposite to the sliding that it is preventing. Same thing here. Rolling friction points in a direction opposite to the slide that it is preventing. So if the wheels were sliding, they'd slide this way, but sliding in that left to right direction is being prevented. So the rolling friction force on the wheels must point that way. And what you can imagine that rolling friction force doing is a little piece of the surface of the track and little piece of the wheel that's in contact with that piece of the track. At that contact point, there are again molecules in the wheel and molecules in that little piece of the track that are forming adhesive bonds with each other. And you can imagine it as the cart tries to move this way. That's the same thing as saying that if you were sitting on the cart, it would look to you as if the track is moving this way. And so when this piece of the wheel is stuck to the track, it's as if the track has grabbed onto that piece of the wheel and gives it a little push to the left. And of course, if you take this point here at the bottom of the wheel and give it a push to the left, that'll make the wheel rotate clockwise. It's that leftward push from the rolling friction force from the track on the wheels that will make the wheels roll, that'll make the wheels spin clockwise. In a case of a car where energy is being sent to the wheels to make the wheels rotate, rolling friction works in a slightly different way, and we'll get to that a little later. But no matter what, whether it's the car where the engine is sending energy to the wheels and making the wheels rotate, or whether it's the wheels of the lab cart that roll just because rolling friction is pushing the wheels in the correct direction to make them roll. Either way, rolling friction prevents sliding and makes the moving thing roll instead of slide. That's the basic idea. Last force is a drag force. F subscript, capital F subscript D is the algebraic symbol for drag force. And a drag force happens whenever something is moving through any fluid, that is moving through a gas or a liquid. A drag force happens when after you hit a baseball and the baseball is flying through the air. A drag force happens when an airplane is flying through the air. If you're swimming, there's a drag force acting on you as you move through the water. What happens whenever you move through, something moves through air or water? Moving this way, the moving thing will collide with lots of air molecules or water molecules. All of those collisions, each of those collisions will be a tiny little backwards push on the moving object. And the net result of all those trillions and trillions of tiny little backwards pushes could be significant. It could be big enough, there could be enough of those little backwards pushes to create a significant net backwards push. And that net backwards push, the sum of all the tiny microscopic pushes from each collision with a molecule, that's the drag force. For an object with a velocity this way, all of those tiny little pushes are backwards pushes. So the drag force, which is the net result of those trillions and trillions of backwards pushes, is always pointing opposite to the velocity, just like kinetic friction was. The interesting thing about a drag force is that it gets stronger as speed increases. Right, the drag force on an airplane while it's on the runway taking off is pretty strong, but once the plane is at its cruising speed, much higher speed than when it was on the runway, the drag force on that plane is much, much stronger. Important point to remember, and we'll come back to this and we'll think about it a lot when we look in a little bit of detail at drag forces, but if you increase the speed, you get a stronger drag force. which kind of makes sense if you think about the extreme case. If you're not moving at all, there is no drag force. Right? At the increasing speed means stronger drag force, so decreasing speed means weaker drag force. Well, that also means that the tiniest speed, speed 0, would give you the absolute weakest possible drag force, 0 drag force. This relationship allows us to use a simplifying approximation in many cases. When the speed is relatively low, then the drag force is relatively weak, and in many such cases, it's so weak, so tiny compared to other forces in that situation, that we can pretend that drag force just isn't even there at all. So usually we will consider drag forces only in the case of an object that's moving at high speed. High speed means big drag force. So just take an example of all of this. Imagine somebody in a bicycle race, long bicycle race, the Tour de France, something like that, and at one point they've been moving across a horizontal road, and now they're starting to come to a hill and starting to move uphill. They've been speeding up all the time they were along the horizontal part of the road, speeding up so that now their speed is high enough that the drag force is significant. And now imagine what happens as soon as they start to go uphill. So there's the cyclist. Moving uphill. What are all the forces on the cyclist? There is, of course, always, well, we'll take the cyclist plus the bicycle to combine them and consider them just to be one thing. That is, we're using that so-called point-like mass model that was mentioned back in Chapter 1. We're not interested in the individual parts of this mass. We're interested only in the fact that this cyclist plus bicycle is some mass that's moving uphill. One force, of course, is the weight. Always pulling straight down, always pulling towards the center of the earth. And then, of course, there's a normal force from the surface of the road. Normal force always points perpendicular to the surface. So perpendicular to this surface would be a normal force pointing that way. And as I just said, the cyclist is at the bottom of the hill, so they've not slowed down very much. They're still moving at a high enough speed that drag force is significant. Drag force always points opposite to velocity. So there's a drag force pushing backwards on the cyclist and bicycle. And, of course, the bicycle wheels are rolling, not sliding. Sliding is being prevented and we get rolling instead. That means there is rolling friction. As the cyclist moves this way, if the wheels were sliding instead of rolling, they'd slide this way. When rolling friction makes something roll instead of slide, that rolling friction points opposite to the slide that it has prevented. The rolling friction is opposing any possible slide, so it points opposite to the slide that you would have had. The slide would have been this way, so rolling friction will point that way. Now, that's how rolling friction works if the cyclist for a moment isn't pedaling. If the cyclist is pedaling, then you've got the same kind of situation as the car. Here, the cyclist when the cyclist is pedaling, is sending energy to the wheels in order to make them roll, just as the engine of the car sends energy to the wheels in order to make them roll. And as I said before, that gives you that makes the rolling friction operate a little bit differently, and we'll get to that later. But here, I was just assuming that for a brief moment, the cyclist wasn't bothering to pedal, was just coasting. Last point I want to make, notice that all of these forces except for weight are so-called contact forces. They're forces that exist only when the thing that is feeling the force is actually physically in contact with the source of the force. The bicycle and cyclist feel a normal force only if the surface can actually push on the bicycle, and the surface can push on the bicycle only if the surface and the bicycle are in contact. The rolling friction force can happen only when the surface that is the source of that rolling friction is actually in contact with the rolling tires. And the drag force can happen only if the cyclist is actually in contact with the air, actually moving through air. So that's the reason for an important piece of advice that you saw in Chapter 4. If you're trying to find all the forces acting on an object, look at the boundary of that object and identify all the things that are in contact with the object. And it's almost for sure that all of the things in contact, or at least most of them, will be applying forces, contact forces, to the object that you're interested in. That's a good way to make sure that you don't miss any of the forces that are present. Look at everything that's in contact with the object you're interested in. All those objects in contact are likely sources of forces on the object.